Good morning, everyone. So in the last lecture, the first lecture of the course, we saw two quick examples of the use of probabilistic method. I was initially planning to do a longer example on a problem called sum-free subsets of numbers, but I thought maybe I'll keep that for later and get into a problem on Ramsey numbers. And this Ramsey numbers will kind of stay with you for some of you who have, I think, done the graph theory course last time, they would have seen this Ramsey numbers. They turn out to be a very how do I call it? It's a good benchmark problem for many modern methods in combinatorics. Okay, a lot of problems get tried, a lot of new techniques get tried against this problem. Okay, so this problem will kind of this variance of this problem, I should say, will stay with us for the rest of the course also. Today we will only introduce maybe the central or the more the first of the problems that are grouped under Ramsey numbers. We will see more problems as we go along. Okay, so let me motivate by asking a few concrete versions of questions from the area of Ramsey theory. Okay, so first question that we will start with is the following: can you two color the edges of a graph, of the complete graph on 5 vertices? Okay, now let me clarify, because we will be using the word two color the edges almost always in this lecture. Okay, we'll use this a million times in this lecture, so please let me define that carefully. Okay, so here when you say two color the edges of a graph, what is meant is you have a bag of two colors, let's say red and green, and each edge of the graph has to be either colored red or green. Okay, every edge should get a color. And importantly, those who have done graph theory, there is a notion of proper edge coloring of a graph, which means two adjacent edges, okay, two edges which are touching each other like this should not be given the same color. Okay, you cannot give red and red to this. This is what is the usual definition of a proper edge coloring. But in this context, this is not, this kind of a requirement is not there. Okay, so we are not insisting that this coloring is a proper coloring. Okay, all you have to, so in fact it is, in that sense it is much simpler than the normal coloring. All you are asked to do is to assign one of the two colors to each edge of the graph. That's all. Okay, there is in fact you can see that if the graph has a vertex with degree 3 or more, okay, then you cannot have a proper two edge coloring. Okay, so this is not about proper edge coloring at all. Okay, and so that's about, when we say two color the edges, this is what is meant. Okay, yeah, now let's get back to the question. Can you two color the edges of this complete graph on 5 vertices? Okay, this is drawn here. This is a complete graph on 5 vertices. It has how many edges does it have? It has 5 choose 2, which is equal to 10 edges. And this 10 edges you are supposed to color using two colors. So how many options are there? There are 2 to the power 10 different possible colorings if you are given two colors and 10 edges. But the question here is, can you do this coloring in such a way that there is no monochromatic triangle? Okay, can you do it in such a way that there is, like our coloring is red and green, so can you color it in such a way that there is neither a green triangle nor a red triangle? Okay, this is the question. So this is a good time to pause, stare at this complete graph on 5 vertices on your screen, and try to do a coloring so that there is no monochromatic triangle. Okay. I mean, maybe if it's difficult to do in mind, you should probably draw a copy in your notebook and then try to do the coloring. Okay, so I'm assuming you have tried, and almost all of you, I'm sure, would have found a coloring which will work. Okay, so let me show you. Okay, so let me color green color using green the 5 outer edges of the K5 in the outer in the way it is drawn. Okay, so what does the green edges together form? The green edges together forms a C5 graph cycle on 5 vertices, and it does not have a triangle. Okay, so the green color class is okay, there is no green triangle. Now the remaining edges I give a red color. Okay, now if you look carefully, you will see that the red edges also forms a cycle on 5 vertices. Okay, it's just that it is drawn in a not drawn in the usual way a 5 cycle is drawn, but this is anyhow still a 5 cycle drawn like a star fashion. Okay, since the red is also a 5 cycle, that also does not contain a triangle. Okay, so the answer to this question 1 is yes. In fact, you can two color the edges of K5 such that there is neither a red triangle nor a green triangle. Very good. Okay, so let's move on to question 2. Now the same question, but now about K6 rather than K5. So K6 is the complete graph on 6 vertices. How many edges will it have? It will have 6 choose 2, 15 edges, right? And so you will have 2 to the power 15 possible colorings. It's a huge number. But the question is, can you do a 2 coloring of the edges of K6 again such that there is no monochromatic triangle? So if the colors are red and green, we should color it in a way such that there is no red triangle and no green triangle. As you have noticed here, monochromatic refers to the color of the 3 edges being the same, which is obvious because the coloring was an edge color. Now again, I want you to pause and think. Okay, I'm assuming you have done that. You would have also thought that even though this can be, I said there are only 2 raised to 15 colorings, going through all that, 2 raised to 15 is a huge number. Okay, going through all that colorings is technically possible. You can do all the colorings and check if there is a coloring which satisfies this condition, but the answer will turn out to be no. But checking all those 2 raised to 15 colorings, right? That's not a quick way of doing it, and not even a smart way of doing it. So let us try to. If you haven't already done it, try to. The answer to this question is no. Okay, you cannot 2 color the edges of K6 so that there is no monochromatic triangle. So now that I have given you the answer, if you haven't already done so, I want you to pause and try to prove why that is the case. Why is it that you cannot do this? Or to restate it, can you prove that in every 2 coloring of the edges of K6 there exists a monochromatic triangle? Okay, I'm assuming you have thought about it, and either you already knew this proof because it's kind of this is relatively a famous result. It is usually known as the party problem. It says that if 6 people go to a party, then there will be 3 of them there will be at least 3 mutual friends. There will be either 3 mutual friends or 3 mutual strangers. Okay, so here 2 people, if they are friends, let's say you put a green edge between them, and if they are not yet friends, if they're strangers. By the way, there are only 2 kinds of relations. If you are not a friend, then you are a stranger. Okay, so if you are a stranger, then you put a red edge between them. So this red green coloring is the stranger friend dichotomy between people. And when you say there exists either 3 people who are mutual friends or 3 people who are mutual strangers, you are essentially saying there is either a red triangle or a green triangle. Okay, so this version of the problem, known as the party problem, is famous in recreational mathematics. So some of you may have seen that. Even otherwise, this is a nice proof. I mean, if you haven't seen this before and if you got the answer, then it's amazing. Okay, it's a short proof, but still, if you could figure it out by yourself, it's amazing. I'm saying all this to entice you to pause further and try to solve it by yourself if you haven't done so. Okay, By the way, the intention of this course, okay, the objective of this course is not to just cover how to see how what is probabilistic method, how it is used, and so on. In the my intention is, or my intention is to what I would like is if each of you would end up proving something of your own. Okay, so yeah, this I'm trying to pitch, trying to do things in this course in a way such that you not only see the proof, but you also see the motivation behind the proof, or why this is done in this way, how somebody, the original person, original mathematician who would have proved that, how would he or she have arrived at this kind of an idea, and so on. Okay, so more than the results that you see here, try to think about how somebody would have come up with such a proof. Okay, so yeah, I'm hoping you will you'll follow these lectures with that kind of aim in mind. Okay, so one essential thing to do is to try proving things yourself as much and spend on it as much time as you can, and only when you really get tired, come back and see how it is done. If some proofs are phenomenally hard, I'll actually tell you that it is really hard. Maybe you should not spend unlimited time there. Think about it for some 10-15 minutes, understand the essential difficulty, and come back. Okay. Yeah, a lot of general talk. Okay. So now we will see a proof for the fact that any two coloring of edges of K6 has a monochromatic triangle. So this is going to be a repeated application of pigeonhole principle in this version. Okay, so pick any vertex of K6. Okay, so let's say the vertex set of K6 consists of 6 vertices. I'll call them V1, V2, V6. Okay, and look at the 5 edges that touch V1. Okay, these are edges to V2, V3, V2, V3, V5, all the way to V6. Right now, you are given 2 colors and you have 5 edges. So pigeonhole principle, or its quantified version, will tell you that at least 3 edges get the same color. Okay, so maybe at least 3 edges get red, or at least 3 edges get green. Easy to prove. Like if there are at most 2 green edges and at most 2 red edges, then there are only total 4 edges, which means 1 edge was left uncolored, which is not allowed. So you either have 3 green edges or 3 red edges. Okay, so just to keep the picture possible, I am assuming that it is the red color which appears 3 or more times incident to V1. If it was green which appears 3 or more times, it's essentially the same proof. Okay, so the endpoints of these red edges, okay, so in this case it is V2, V4 and V5. In general, I'll call them VA, VB, sorry, not this is VA, VB and VC, right? So these are the just to keep the color consistency, VA, VB and VC. This is step 1. Okay, so you have now in the proof, this V3 and V6 will never be used again. Okay, so in the remaining proof, the graph that you are considering or the graph that you are considering only has 4 vertices. You have this V1, you have this VA, VB and VC, and these 3 edges we know are of red colors. There are 3 more edges to consider, this, this and this. We as of now do not know what their color is. We are going to argue that there is something more that can be said about the color of these 3 edges. Okay, so suppose among these 3 edges even one of them is red. Okay, even if one of them is red, then you have a red triangle here, right? That's what you remember. Remember what the aim that we have. Our aim is to show that there is a monochromatic triangle. So once you get a red triangle, you are done. Okay, so among these 3 edges, even if any one of them, if it is red, then we get a red triangle. Okay, if VABC was red, we would get this red triangle. Okay. Which means now the only case left is when all these three are not red, which means they are of the other color, green, right? And if all three of those edges are green, then you get a green triangle, and hence in any case you end up having a monochromatic triangle, and that completes the proof. Okay. Now, let me make two remarks here. You have to contrast our arguments to question 1 and question 2. Okay, both questions were of the same type. Was can you color some Km, to color the edges of Km so that there is no monochromatic triangle. In the first case, your proof was just giving this example, the example being this particular two coloring of the edges of K5. That's because it's a yes answer here, when you say there is only one K5, and hence giving one coloring which satisfies the condition is enough. Whereas in the answer to question 2, we had more of a proof by cases, right? We analyzed instead of trying to run through all the 2 to the power 15 cases, we used a very clever and systematic approach to attack it. Okay. Now, I could have asked a similar question with a triangle. Instead of a triangle, I can put like a K4, okay, complete graph on 4 vertices, or even a K5. So this number will also correspondingly change. Okay. So these two questions here immediately can be generalized into an infinite list of questions, right? I can pick any, I can replace this triangle here with any kk, right? K equal to 3 is the current question, and correspondingly this K5, this 5 will change, or this 5 will change to something larger. Okay, so you already get an infinite list of questions, and we will see if any of these methods can be generalized. Okay, let me give the spoiler alert right away. Actually, the method that we use to solve question 2 can indeed be generalized, and we will see that immediately. Whereas this kind of coloring is not that easy to generalize, and that is where the application of probabilistic method will come in. Okay, it will be of this form. It will be a way to find a two coloring which does not have monochromatic KKs, monochromatic complete graphs of the given size. Okay, so that will come after some 15 minutes. But before that, let us try to generalize the approach we did here. Okay, yeah. So can we generalize these to larger monochromatic structures? So I'll change this 100 later on after I figure out this how to generalize our answer to question 2. But 100 is, I'm putting this 100 as a large enough number so that you have enough vertices to do pigeonhole principle as many times. Okay. So again, the question is, can you two color the edges of K100 so that there is no monochromatic K4? Okay. Here I strongly encourage you to pause and try to do the proof yourself. This is essentially a generalization, or this will go similar to this idea that we have used here, but you may have to do that repeatedly. Okay. So remember, if you just to get a vertex, if you take a vertex V1, since the graph now under consideration is K100, there are 99 edges incident to V1. So at least by pigeonhole principle, at least 50 of them are of the same color. So within that 50, you can either get a triangle or a K50, which is monochromatic, right? Because among those 50 vertices and the 50 choose two edges between them, even if one of them is red, assuming that red is this color that appeared 50 or more times, you get a red triangle. Otherwise, you get a green K100, sorry, a green K50, right? But that's not what we want. We want either a red K4 or a green K4. Okay. So green K100 will give a green K4, but a red triangle will not substitute for red K4. Okay, that's why this proof in one step will not work. But you should try to do that. Still, it is possible to extend this proof. Okay, so I'm assuming you have. I'm kind of thinking maybe most of you would have actually got this proof. Okay, so let me explain the proof. V1, as I told you, has 99 edges incident onto it, which means at least 50 of them are of the same color. Okay, now when I say there could be much more than 50 of them, but I only want this lower bound guarantee on the number of red edges. So the other endpoints of those red edges, okay, which I have marked here, okay, these endpoints, okay, let me call them as N1. So N1 is a subset of vertices of this K100 with the property that the edges from any vertex from N1 to V1 is colored red. Okay, in this case red. If it was green, it was the same argument. Repeat. Okay, and we know that the size of N1 is at least 50. Okay, so yeah, this is N1 be the endpoints of these edges. Okay, now you pick a second vertex. So that's what we are doing the same technique again. We pick a second vertex, but we pick it from within N1. Okay, this second vertex has to be, in fact, for the rest of the proof, the only vertices that are under consideration are V1 and all the guys in N1. The remaining guys here are no more under consideration. You can even delete them from your mind. Okay, so now among you pick a vertex V2, any vertex V2 from this N1, and then look at the edges, which go to the remaining vertices inside N1. Remember, the guys outside have been deleted from your mind, so don't even think what happens to the edges which go to them. Okay, so you have at least 24 such edges, right? Because N1 is of size N1 is of size 50, so there are 49 edges incident to V2, which means by pigeonhole principle, at least 25 of them get the same color. Okay, so at least 25 edges from V2 to remaining vertices in N1. That's important, you know, this to N2, the remaining vertices in N. Okay, again, there's a small typo there. I should have said to the remaining vertex in N1. Okay, has the same color. Okay, now we consider two cases. One is the fortunate case, which we are hoping for. Suppose this color, which appeared 25 or more times, that also turned out to be red, the same color as what we picked in the first step. Remember, in the second step, the color that can appear maximum number of times can either be red or green. So this does not cover all the cases. In the next case, we will see what to do if this was green. But suppose here also the color that was repeated multiple times was red. In fact, you can complete this proof if there are at least 4 reds, but we will do all those optimizations later. So suppose this is the case, right? So now you, among these edges that go from V2, look at those edges which are colored red. There are at least 25 of them. Look at their endpoints, and that's what you call as N2. Okay, that's your N2. So what is the property of vertices inside of N2? Since they all have their edges that go to V2 is all colored red, that's because of the second pigeonholing principle. But this N2 is actually a subset of N1, right? Because we deleted everything else, which means they share the property that N1 shared, which is that the edge to V1 is also colored red. And the edge between V2 and V1 is also colored red because V2 was part of N1. Okay, so this is the structure that you get. Okay, this indicates that all the edges that go from V2 to N2 and V1 to N2 are all red. Okay, so this is the idea, and by the counting, we know that N2 has size at least 25. Now, if you recall the earlier argument, even if one edge, so there are 25 choose 2 edges here, but even if one of it happens to be red, then you say some VA, VB, then you see that V2, V1, VA, VB forms a red K4. All the 6 edges there, 1, 2, 3, 4, 5. 5 edges of the 5 out of 6 edges are already red. We have argued if there is one more edge which is red, then you have a red K4. Otherwise, what do you have? You have a green K25 which contains a green K4 for sure, right? Hence, in this case, the proof is complete. We either get a red K4 or a green K4. But this is the fortunate case where the pigeonholing gave a large number of red edges incident on V2 to N1. If it was not so, okay, if it turned out that when you looked at V2, this was V1, this was V2, right? So when I looked at V2, you did not get 4 edges even, okay? So but like forget about whether it is 4 or 25. It's we have to apply this pigeonhole principle, and then we will kind of skews it, okay? By the way, remember that you may wonder, okay, why do you really require 25? All that you require, if you look at this proof, is 4, and that is true, but we cannot even say that there are 4 red edges. It may be the case that 48 of them are green, right? So yeah, so V2's dominant color into N1 is green, but then you still identify this set N2, which are the endpoints now of the green edges, right? So this N2 is still a subset of N1, okay? But now what do? Now you repeat this process one more time. You pick a V3 from within this N2, okay? You pick a V3 from within this N2, and then you see its edges. Remember, all the other vertices in the graph except V1, V2 and those in N2 are deleted. So now you focus your attention to the edges from V3 to rest of N2. Since N2 has 25 vertices and V3 is one of that, there are 24 such edges. By pigeonhole principle, at least 12 of them have the same color. Okay. Now again, once you see they are of the same color, you have to analyze both the cases. Case 1 is when they are all of color red. Case 2 is when this dominant color is green. But in both cases, it's not very different now. Okay. So we are going to pick this further subset. We're going to again split this into. We are going to pick this further subset N3. The property of N3 is that it is of size at least 12 and all the edges from V3 to N3 are of the same color. Okay. Now, if this color from V3 to N3, it is red, okay, the first color that you pick, then you get this kind of a picture, okay. Now you kind of ignore V2. Instead of V2, you have V1 still. I kind of, drew the, maybe you can just to keep a this V1 and V2, I'm just trying to keep the same picture. So in place of V2, you replace it with V3. That's the idea. Now V1's edges to N3, because N3 is a subset of N1, remember, are all red. V3's edges to N3, because of this third step, the pigeonholing in the third step, they are all red. Edge between V1 and V3 is red because V3 is a member of N2, which is a member of N1, right? Hence, this is also red. Now, even if you get one red edge here, you get a red K4. Otherwise, all the edges here are green, which means you get a green K12, which contains a green K4, so you are done. In the other case, if in the third iteration, if the dominant color was green, okay, which means V3 to N3, N3 is at least 12, V3 to N3 edges were all green, then you forget about V1, but pick V2 and V3 together, okay. So you pick V2 and V3 together, and then you see a green structure like this. Why? Because this N3 being a subset of N2, all the edges it sends to V2 is green. All the edges that N3 sends to V3 is also green, because that's the case that we are considering. V3 to V2 edge is green because V3 is part of N2. Okay, so you get this green structure. Now how do you complete the argument? Even if the one edge here is green, then you get a green K4, otherwise you get a red K12 which contains a red K4, right? So with this we have completed the proof. We have exhausted all the possible cases and shown that in any of the cases we can guarantee either a red K4 or a green K4. Okay. Yeah, in all the cases we can do. Now you would have seen that this 100 was too much, right? You could have made the same claim with a smaller number, okay? And this is an easy exercise. I want you to figure out how small a number can I write here instead of 100. Can I write 50? Can I write 25? Where would be? So how do you figure out such a number? You essentially work the proof backwards. You look at, I want you to again pause and figure that out number for, figure the number by yourself, assuming you have done that. Okay, you essentially work this proof backwards. In this step, you don't need a K12 here. All you need here is a K4. So you want your size of, the size of your N3 to be at least 4. Okay, which means to get 4 vertices of the same color here, you want your N2 to be of size 8. Okay, if N2 is of size 8, then you pick V3. There are 7 more edges. If there are 7 edges and 2 colors, that's the smallest you need to guarantee that there are 4 edges with the same color. No, you don't need 8. 7 is enough because there is no 3.5 happening here, right? So you need 8 edges in N2, which mean this is the same case, right? I mean either this or this, which means in N1, in order to get 8 vertices in N2, you should have this is one V2 is one edge among N2. Remaining you should have 16 minus 1, 15 guys. So you add V2 also, it becomes 16, right? So N1 should have at least 16 vertices, which means this N1 is already obtained after a pigeonholing. So this V1, the edges, the total number of edges here should be larger than 31. Edges should be larger than 31, which means this instead of 100, if you have 32, it will still work. Okay, yeah, so this is the argument. So if you are looking for what is, instead of K100, what Kx can you write? You can put K32. Okay. So any 2 coloring of the edges of K32 will contain a monochromatic K4. Okay. By the way, this 32 is not the smallest, the 32 is not the smallest number you can put in there. In fact, you can put in 18. But this proof is not strong enough to show that, right? There are, by the way, this proof is originally due to, or the generalization of this that I'll state is due to Ramsey from 1930. Okay. So yeah, let me state that and then go. But now once you have shown that 32 is enough, you can put your conclusion as any 2 coloring of the edges of K32 will contain a monochromatic K4. Remember that there is a hierarchy or there is a monotonicity to this number, right? If I can make this conclusion for K32, then it remains true for any number larger than 32. Okay, because it contains K32 as a subgraph. If you, let's say you're talking about K35, then any 2 coloring of the edges of K35 involves 2 coloring of K32s, and hence this claim is true. So you are looking for minimizing or reducing this 32 to as small a number as possible. Okay. So what Frank Ramsey proved in 1930, actually Frank Ramsey kind of used this problem in a very interesting context. Again, Wikipedia is a good source to learn about it. He was wondering about whether you can have total chaos in the world, or whatever arbitrary things you try to do, there would be some regions where there is a nice structure. So he was motivated, I think he was a priest, he was motivated by a lot of theological / philosophical questions. But this, again, as I told you in the beginning, this turned out to be a fantastic benchmark problem to test many methods in combinatorics. So yeah, he essentially showed this kind of a proof that we saw there, and then showed that any 2 coloring of the edges of k, some f of n will contain a monochromatic kn, where this f of n is something like, if you extend this proof, I want you, that is your job, okay, you have to do that as an exercise. Maybe we will discuss it in the tutorial, but I assume you will come to the tutorial after having shown this, right? If you extend this proof, you will get some number like this, 2 to the power 2n minus 5 times n. So if you are looking for kn, you have to do nearly this recursive pigeonholing, you will have to do nearly 2n times, not n times, because only if you do 2n times, every time you do a pigeonhole principle, the colors that go into the further subset we know are the same, but it could be either of the two colors, right? That's why you need this two things. But you can also, the last step you can change. You really don't need to reach an n-sized subset in the end. You are allowed to do this process 2 more times, and you can replace that and then show that instead of this 2 to the power 2n minus 5 times n, you can do 2 to the power 2n minus 3. Okay, so this will be better than this bound for all n larger than 4. Okay, so yeah, I at least want you to do this and do this as an exercise, and this also think about how you can improve that to this number. Okay, and this the smallest number for which, the smallest function fn which satisfies this relation. Okay, here the fn is kind of fixed, but can you do a smaller fn? Okay, and the smallest fn for which you can do this, right, that's now denoted as capital Rn in honor of Ramsey. Okay, so Rn is a function from natural numbers to natural numbers. What does capital R of n denote? It denotes the smallest integer. Okay, it denotes the smallest integer such that any two coloring of this complete graph on Rn vertices contains a monochromatic copy of K. Okay. So this Rn in honor of Ramsey is called the Ramsey number. There are other variants of Ramsey number, but this is the standard Ramsey number. Okay, this is the Rn is the nth Ramsey number. So we saw our question 1 and question 2, if you put them together, it will tell you that R3 is equal to 6. Why? Because any two coloring of K6 gave a monochromatic K3, but that's not enough. That will only show that R3 is less than or equal to 6. But how did we show that the 6 is the smallest integer such that this is true? That is because if you had K5, there was a two coloring which did not have this property. So 6 was the smallest n for which you had this property, and hence this is the, if you put question 3 and 1 and 2 together, this is what you get. Now R4, we neither showed the lower bound or the upper bound correctly, but it can be done in one class, right? But it won't be an application of probabilistic method, so at least I'm not doing it straight away. Maybe sometime later in the course I might end up doing that. So your R4 will turn out to be 18. All that we have proved is that R4 is at most 32. So in order to prove that R4 is equal to 18, you should prove two things. You should first show that any graph on K18, any coloring of two coloring of the edges of K18 will leave a monochromatic K4, and you should give one coloring of K17, two edge coloring of K17 which does not have a monochromatic K4. Now just to look at these initial cases, what is R2? What is the minimum n so that any two coloring of Kn has a K2? You can see that this is nothing but 2, right? Because this K2 is just a single edge, but now if you have to two color K2, it essentially means you color that edge either red or green. In either case you have a monochromatic K2. Okay, and this is kind of vacuous. To get a monochromatic K1, even if there is no edges, there is only one vertex, you still get that. Okay, yeah, these are uninteresting. These are the more interesting thing. But the question is, how does it grow? Okay, by the way, even the next Ramsey number R5 is still an open problem. In fact, anything larger than this is an open problem. You know that this R5 is somewhere in the range, I think 43 to 48 and so on, but you don't know this value exactly. This was a very favorite problem of Paul Erdős, the person known as the father of combinatorics, or at least the father of modern combinatorics. Combinatorics is really an old subject, goes back to maybe 1,500 years, and India can take a lot of pride in having done this. In the ancient history, there is interesting combinatorial work done in India, finding n choose k, finding the number of subsets, and so on. But yeah, let's come back. Erdős is told to have made a nice story about this R5 and R6. Okay, he said that if suppose aliens descend down, fierce aliens descend down to Earth and give you this condition, right? You either tell them the value of R5 or you will destroy the Earth. If they give such a threat, then he says that in order to find R5, maybe you should stop thinking about them using pen and paper. You get all the supercomputers in the world and program them and try to search and find out what is R5, right? So maybe you will try with all the colorings of K43, K44 and so on, and then try to solve the answer. Then he continued the story and said that instead, if they had asked for R6 and not R5, then it is more efficient. It's better than pooling all these supercomputers and trying to solve the problem. It is more efficient to pool all the armies in the world and try to fight the aliens. Okay, so yeah, that's the kind of difficulty that Erdős thinks there is that is there to find out even R6. Okay. So the proof that was left as an exercise, that generalization essentially tells you that this Ramsey numbers grow at most like 4 to the power n. Okay, this 2 to the power 2n minus 3 is upper bounded by 4 to the power n. So it is exponential with the base of the exponent being 4 at most. Okay, we are not saying it will grow like this, and the main question for us is to give a lower bound here. Okay, can we have something which is matching with this upper bound? Okay, how fast does Rn grow with n? And Erdős in 1947 showed that you can put this lower bound is also exponential, but with a smaller constant there. It is root 2 to the power n versus 4 power n. Okay, so this is a significant difference if you think about it. If you try to plot these two numbers, you will see that the gap is very, very huge. Okay, although the expressions look very similar because they are exponents, they are exponentially growing terms. The compound interest rate, okay, this is something like 44% interest, 1.414, right, 41% interest, whereas this is compounding with 300% interest. So these both grow exponentially, but very different exponentially. And one of the biggest problems in this area is to try and narrow down this gap. Some progress has been made with considerable effort, but still there is almost the same amount of gap left. Okay, and the proof of this, okay, my time planning was bad. I was talking too much in this lecture. I should try to control that. So the proof, I think we will have to postpone to the next lecture. And this is going to be the proof of this is going to be the application, one of the applications of probabilistic method that I wanted to illustrate. And this is probably one proof which made probabilistic method quite popular. Okay, this is not the earliest application of the probabilistic method. That is from 1936 in another problem, which we may also see sometime. But this is the proof. This is the application which made it most popular. So you will see this proof explained in any YouTube lecture, first lecture on probabilistic method. But yeah, we'll have to wait till our third lecture to see that. Okay, so yeah, see you next. Thank you.